So what I'm going to discuss inside of this video is trying to find linear approximations for estimating numbers. The idea of a linear approximation is basically that for any function, that if we draw the tangent line, what you'll notice about the tangent line, this thing right here, right, okay, is that the tangent line is actually very close to the function near the point of tangency, okay? So what we're going to do is we're going to use a tangent line to approximate the function. So let's suppose that we wanted to approximate f of x equals x squared minus 3x plus 7 near x equals 1. So what we want to do is we actually want to construct the tangent line, and that tangent line is going to become something called a linearization. So let's recall that the tangent line is going to be y minus y naught, and it's going to equal f prime derived at x naught, okay, and that'll be, in our case, x equals 1, times x minus x naught. And that's just our slope, our point slope form, along with the derivative at x naught. So if we wanted to find that line of tangency, all right, what we'd get is we'd first find f of x naught, which is our y naught, and that's going to equal 1 squared minus 3 times 1 plus 7. So that'll equal 5. And then we want to find f prime at x naught. So let's find f prime of x. That's going to be 2x minus 3. Okay. And so f prime at 1 is going to equal 2 minus 3, which equals negative 1. So my tangent line, okay, is going to I'm going to end up plugging it in to find the tangent line. Now, when we talk about a linearization, there's actually a formula for the linearization. It's actually just a rearranging of this thing here, and a substituting for f of x naught. So the linearization L is going to equal, we're going to say it's going to be y. L is equal to y, which is equal to f of x naught plus f prime of x naught times x minus x naught. And this is called the linearization of f at a, or in our case, the linearization of f at x naught, at that point x naught. So I'll take this and I'll say, okay, well, L then is going to equal 5 plus negative x times x minus 1. So this means that L will end up equaling, that's negative 1 times x minus 1, is going to end up equaling negative x plus 6. And so that's what our linearization is. That's L. There it is. So when we talk about a linearization, what we're talking about is the tangent line. It's finding the tangent line. So that's a pretty simple concept. The idea here, though, is that we're going to use that in order to estimate values for the function. So let's do a little bit of that. So we'll find our linear approximation for f of 1.05. Instead of using actually the value of the function, although we know that we can do that, instead we're going to use the linear approximation. So that's going to be negative, right, 1.05, because that's what x is, plus 6. So that ends up equaling 4.95. And that's the linear approximation for f of 1.05. How about one for f of 0.99? Again, it's pretty close to 1, and so consequently, it's a good one to use for linear approximation. L is thus going to equal negative 0.99 plus 6, and so that ends up equaling 5.01. And there's that. So we've got these two, and that's all you got to do. So once you've found that linear approximation, you basically plug in the values for the linear approximation, and that gives you, plug in the value into the linearization, and that gives you your linear approximation. Okay? Now, important, the value for x must be close to the point of tangency, all right? So remember, the linear approximation is only good if we're close to the point of tangency. If you're not close to the point of tangency, then you can't use the linear approximation, because the linear approximation would end up being really far away from the point of tangency. So suppose that we wanted to know the values of x that will have our linearization within 0.1 of the actual function. right? So let's say, for example, this is one of those things that we want to do. We want to actually create an error bound around the values of the function, right, of 0.1, and see what values of x will actually allow us to be within that value. So let's take a look at our function. Our function is f of x equals x squared minus 3x plus 7. And our linearization is going to end up being, okay, linearization will be L equals negative x plus 6. And the question is like, we want to get the furthest distance between these two. The furthest distance between these two around 1 is 0.1. So if you kind of remember, we talked a bit about this inside of limits, is you could actually write this as it's the absolute value of x squared minus 3x plus 7 minus, and this will be negative x plus 6 is less than 0.1. Okay, so we could actually determine, right, what values of those, okay, or within that, what value of x would actually make this true, right? So we rewrite this, that'd be the absolute value of x squared, okay, minus 2x plus 1 is less than 0.1, okay? And we could solve for x, right? So basically what that would mean is that would mean x squared minus 2x plus 1 is less than 0.1, or x squared minus 2x plus 1 is greater than negative 0.1, okay? And that's all we'd have to do. We'd have to go in, we'd go solve that. Or we could do this by graphing. This, of course, is going to give us an estimate or a really good guess, okay? And what that would look like is that would look like we'd graph, okay, x squared minus 3x plus 7 minus 0.1. We'd also graph negative x plus 6, our linearization, and x squared minus 3x plus 7 plus 1.1. Okay, so what we want to do is figure out where is our function between these two graphs. Okay, these two graphs. So let's do Desmos and we'll see what that looks like just really quickly. Okay, so if we take a look, the red line, that's our linearization, right? It's the line. Then the first line is when we subtracted 0.1 from our original function, x squared minus 3x plus 6.9. And the second one is x squared minus 3x plus 7.1. We added 0.1. And you can see that there's a boundary here where our line, our linearization, is actually in between the blue line and the green line. Okay, so that's going to be the area, right? That point right here where we got the intersection with the blue line and the intersection with the blue line on the top, okay, it's going to be the area where we have that boundary. Now, this is going to give us actually a pretty good sense here, okay, because Desmos is great like that. All right, we go in. I'm going to take this. All right, there we go. And that actually is the point of intersection. 0.684 is our value for x. And then we'll choose, there's the second point of intersection on Desmos. And you can see 1.316. Now be careful, it's not going to include those two, so it's going to be our open interval. So it's going to go from 0.684 to 1.316. All right, notice this is the place where we are both above the blue line, which is our lower bound, and below the green line, which is our upper one. So I'll put this in, and actually it'll end up being 0.684 to 1.816. And that is the boundary where our linearization is within 0.1 of the function. So when we're asked to find, okay, suppose we wanted to know the values of x that will have our linearization within 0.1 of the actual function, right? When we're asked to find this, what we're actually being asked to do is to kind of basically construct this absolute value. We want to determine the distance, okay, between these two is at maximum of 0.1. Sometimes we can do this algebraically, but sometimes we have to do it graphing. And if we do it graphing, what it's basically saying is it's saying, okay, take the function, subtract, take the function, subtract the bound or the error bound, and then take the function, add the error bound, and we want to figure out, use it graphically, where is our function, right, our linearization in between those two error bounded functions, okay? And there it is. We found that it was 0.684 and 1.816. You can also use your graphing calculator to do this kind of thing too. All right, so that concludes the lesson. Linearization is a technique for estimation. It's utilizing the derivative to do estimation, right? And basically, it's finding the tangent line. We go out, we find the tangent line, and that gives us all the information that we need.